So I propose that we start. So I'm very glad to introduce Professor Andrea Marin of the University Ca' Foscari in Venice. So Andrea Marin has lots of activity in stochastic networks, queuing theory, scheduling, and is interested in various problems in conjunction with data centers and virtual computers offered to everybody on Earth. And so today he will describe recent work on job migration in queuing networks. Please.
So thank you very much. Good afternoon, everyone, and thanks for being here. So today I'm going to talk about queue networks, and in particular job migration in queue networks. So job migration are not like novelty in queue networks. Jobs actually move from station to station in queue networks, but we will see different type of movement, mainly with the goal of obtaining load balancing in the queue network. So, okay, gonna use this. Okay, so this is the outline of the talk, and we're going to go with some motivation and goals. Then we will present a first model with some example, and then a second model. Okay, so again, the main goal will be to achieve load balance in a system. So let's consider a queue network. Okay, is everyone familiar with queue networks, or someone who on problems? Okay, so we consider a queue network. The very basic queue network with a tractable solution is the queue networks known as Jackson or Gordon-Newell type. Jackson if it's the open network, Gordon-Newell if it's the closed network. In these models, you have n stations, and all customers are statistically identical, so we are in single class. The service times are distributed according to an exponential random variables, and these random variables are independent of everything else. We have routing among the station of the queue network. This is a probabilistic independent routing. And if the model is open, you have arrival from the outside, and the arrival from the outside follow a Poisson process. Okay, so that's actually a very well-known result. So these type of systems are interesting because they have an exact solution that is very well known. So basically, you are able to identify some functions, gi of ni, where I is the index of the station, okay, and the joint stationary distribution of the state of the network, so the probability of seeing a specific state at each station, okay, is given by the product of these functions that are dependent only on the state of that station, okay? So that's pretty simple to compute. Here you have a normalizing constant. If the network is closed, if the network is open, the normalizing constant is very easy to achieve. And when the network is closed, there are several algorithms to compute the normalizing constant without generating the entire state space of the network that would lead to a combinatorial problem. Very similar is the result for open networks. Here you see I omitted the normalizing constant because it's very simple to obtain the normalizing each component in isolation. Then you have the normalization of the model. So this is what is really well known from the literature. So what do we propose here? So suppose that you have queue networks in which some services are replicated, so they're offered by more than one station. Okay? Intuitively, you would like that the services that are offered by more than one station, they have roughly the same load factor. So the utilization of these services should be the same. Why? Because this will ensure you that the bottleneck does not appear in one of these services, leaving the other one maybe not completely utilized. So ideally, you would like that all equivalent nodes, so nodes offered in the same service, should have the same load factor, so the same utilization. Okay? So we propose two ways of reaching this. One is the load balancing network. And the idea is that you want to move the jobs from a heavy loaded station, okay, to a station that is in that moment without much work to do, or is idle. Okay? Then we say another way of achieving this, which is the fetching queue networks. This is a little bit more specific because we assume that some services can be skipped. Okay, so suppose that you have a filtering mechanism for example, replying to a query on a big data set. This have several stages of refining to obtain the reply to the answer to the query. But if you skip some filtering phases, the quality of the result is lower, but sometimes this is done for performance reasons. So for example, to maximize the throughput of your system. For all these methods, we are looking for conditions that allow the analytical tractability of the model, so for models that are in product form. Let me mention that the model of load balancing networks is the result of a work with Jean-Michel Fourneau and Simonetta Balsamo, and the work on fetching queue networks is the result of work with Diletto Ogliaro, Sabina Rossi, and Giuliano Casale. So, approaches for load balancing from the literature. So basically you have two ideas for making dynamic load balancing. The first view is this. I am a station, I'm overloaded because my buffer begins to be too big, too long, okay? So I cannot offer reasonable response time in that moment. And I look for another station that hopefully is less loaded in that moment, and I transfer to this station some of the jobs that I should serve. So I reduce my backlog, I increase the backlog of the other station, but in this way, I try to balance the workload that you have to serve. Okay? This approach is known as sender-initiated. So it's the station that is suffering a heavy load that takes the initiative to send some of the works or the jobs in its backlog to someone else. The other approach is the receiver-initiated. That is a station in which I'm not doing much because I don't have a backlog to work on, and so I start asking someone else if they have jobs to send me so that I can help their work. Okay? That approach is known as receiver-initiated. These two approaches have been studied by simulation some years ago by Lazowska, and the results of these studies is that maybe in a counterintuitive way, the most effective way to reach load balancing is the receiver-initiated strategy, not the sender-initiated strategy. So it's better if the station that is in a certain moment with nothing to do to start looking if there is some other that needs to send them some jobs. To me, my intuition when I began to work on this was that service-initiated should have been more effective, but in fact, you can see that this is not the case. So,
question.
Yeah.
So, I mean, you're interested in policies which the product form was steady state, right?
Yes.
So you're interested in policies that have a steady state, and
yes.
And you want the load balancing in the steady state.
Yes, exactly. Yes.
Okay.
Yeah.
And
in the long
principle,
run.
you don't preserve product form when you do load balancing, do you?
I do preserve product form. That's the non-conventional result that we are going to show. We're going to show how you move a batch of customers from another station where state is larger than yours, let's say you move it in a batch way, okay, and still you maintain the product form. That's the kind of result that you are going to see. Okay, good. So we will work basically on receiver-initiated strategy. So let's see LB networks. So this is an example of queue network. Here you see that I have 3 databases that have some kind of routing. This is taken from the paper that we wrote, and I don't tell you all the story behind this network. But basically, these 3 stations offer the same service, their database, okay? And these 2 stations offer the same service. Okay? The goal is to have a network in which, by exchanging customers, you're going to have that the load factor of these 3 stations must be equal, and the load factor of these 2 stations want to be equal because they are stations that offer the same type of service. So there is no reason why one should be more loaded than the other one. Okay, so how do we move? This is the policy of job migration. So the idea is this. When a station becomes empty, it starts an exponential timer, okay? And 2 things can happen. Either the timer expires and the station remains idle for the whole length of this timer, okay? And in this case, it will fetch some jobs from another station, okay? Or another job arrives, the station is not idle anymore, and the timer is forgotten, so you don't fetch any jobs from other stations. Okay. The question now is how many jobs do you steal from the paired station? The number of jobs that you steal is geometrically distributed, okay, but truncated to the number of jobs that is present at the station that you are polling. Okay. So let's say that this is the geometric random variable. Okay, you sample 5, but the station that you're polling has only 3 jobs. You fetch from that station 3 jobs. You can't fetch 5. Okay, so that's why there is this truncation on this distribution. Okay, if this Bij, which is basically the parameter that governs the size of the batch between I and j, is equivalent, it means that you're just stealing all jobs from the station that you poll. Okay, pretty simple, right? So some problem to solve. So what should be the frequency of this timer that measure the amount of time that you stay in state 0? How do I decide the length of this timer? And how do I decide the parameter of the geometric batch that I'm going to steal? These are the 2 main problems. And the third problem that is connected to the first 2, because once we achieve analytical tractability, we're able to answer to question 1 and question 2, is can I maintain product form in with this strategy? So let me first show you what should look like the load factor of a station. So the load factor consists of, these are the flows that arrive at the station, okay? And this is basically the service rate. So why customers arrive at the station? First of all, from all other stations, different from I, you have a flow arriving at station I. This is the ordinary routing of queue networks, okay? Then you have another flow arriving. That is the flow that arrives because you are polling another station and you steal some jobs from that station, second flow. The third flow is the flow from exogenous arrival at the station. So for the outside, new customers may arrive if the network is open, and they arrive with that intensity. At the denominator, we expect to find the service rate of the station, which is the rate at which you just send out the jobs because you've serviced. And then we have another factor, that is the jobs that are stolen to you because some other station has polled you. Okay, so this is basically the station K polling station I, okay, and this is the flow going from station K to station I due to, so from station I to station K due to fetching of stealing of customers. Okay. Once you have this, you can prove, there are actually two ways that we have proved this result. The first way is by using the reverse compound Argent theorem that gives a very nice and elegant modular proof that from the equation that you saw before, product form comes out right simply. Or you can try to do it with solving the system of global balance equation. So basically, the theorem says, if you can find a solution to this system of equations, okay, then the network has a Jackson product form, basically, in which rho I is not anymore lambda I over mu I, but is the solution that you obtain within this, with this formula using the solution of the system of equations that are here. Well, first we notice that this system is a system of nonlinear equations. Okay, so if you're used to Jackson theorem, you know that the traffic equation form a linear system of equations. Here we have a nonlinear system of equations. That's not so surprising for people working in product forms, because we know that from G-networks or from that that's not surprising that some policies of routing they bring to have a nonlinear relation among the system of equations. But there may be cases, differently from what happens for example, G-networks, in which this system of equation does not admit a solution. Okay, we will see later when this happens. But remember that here you may notice that this is the polling rate, and the polling rate must be equal to this unknown over here. Okay, so the things that we propose is this: leave the polling rate, so you have basically the product form only from a specific polling rate. Okay. So the point is, leave the polling rate as an unknown. So don't fix the polling rate because you don't have product form for any polling rate. Okay. Find the condition for the product form, so for having a solution to that nonlinear system of equations, and then you get your polling rate. Okay. And want to say, yes, but with that polling rate, which relation do I obtain between the load factor of the queues that I have paired together, right? Okay, and that is actually an interesting thing, because the relation that you obtain is exactly this. So the ratio between the load factor of Qj and Qi is going to be equal to the parameter of the batch distribution that you have used to steal the jobs from the queue. Okay? So this means that if I set Bji equal 1, which is the practical case because we want to reach perfect load balancing between the station, okay? So basically we steal all jobs of the polled station. It means that with the alpha obtained by the product form condition, the two stations are perfectly balanced. Okay? So we think that this is a nice thing because the mathematical condition that comes up from the product form is actually the same things that you would like to reach. So it's exactly the rate that you're looking for to pair the two stations with the same load balance. Okay, yeah.
So you have this set of nonlinear equations. You said it did not always have a solution, but is there uniqueness of the solution if it exists?
Yeah. Now with yes, you've got that. You know the rate. Yes.
You know the rate. Yeah.
Yes.
So if it exists, it's
yeah, it's exactly the one. Now we see the cases in a simple example of why it may not exist. Okay, so let's suppose very simple case. We have two independent queues. Okay, lambda 1 over mu 1 is the load factor of the first queue if you don't balance them. Lambda 2 over mu 2 is the load factor of the second queue if you don't balance them. Okay, so the first solution is don't do polling. Okay, so if station 1 doesn't poll station 2 and vice versa, clearly everyone maintains its own load balance, and that's absolutely not interesting. Okay, but this is a solution of the system of nonlinear equation. Okay, it's just a trivial solution that we want to avoid. Then suppose that we have B12 and B21 between 0 and 1. You can show that the solutions are either x12, this is the polling rate from station 1 to station 2 equals 0, and x21 equal to this expression over here, or vice versa. So one of the two must be 0. What does it mean? It means that if you want, if you set up your system in such a way that the load factor of a station is 0.8, the load factor of the other station is 0.6, and you want that the station with 0.8 polls the station of 0.6 to reach a certain balancing, that's impossible. And the system of nonlinear equation doesn't admit to solution. Okay? So, and that's reasonable because you don't want a heavy loaded station to poll someone that is less loaded. But if you allow them to reciprocally poll each other, okay, then it turns out that one polling rate is 0, which is the one from the heavy loaded to the low loaded, while the other one, you will get a real number that is actually the polling rate that you want to have. The case, the interpretation is exactly what I've just said, but the case that we like more is the case of B12 equal to B21 equal 1, so they must be equal. Okay, so it means that we want the two stations after balancing to have the same load factor. Okay, and what you've got is that the solution is this one. Okay, as you may see, this describes an infinite set of solutions. What does it say, this one? It basically says that it's convenient to set this rate equal to 0, because you want to minimize the migration of jobs for load balancing, and the station with the lower load factor will poll the other one with a timer that is given by this expression. By the way, since the system of nonlinear equation may be tricky to be solved symbolically like we are doing in this simple case, there is an algorithm that I'm not going to present today, but that finds the solution with an iterative method, and it finds a numerical solution to the rates that you are looking for. Okay? So, numerical example. Stay with this system, it's very simple. Suppose that lambda 1 is equal to 0.8, lambda 2 is equal to 1.2. Here we have mu1 equal 1, mu2 equal 2. Okay? So basically, this station here, station number 1, is more loaded than station number 2. So the load factor without load balancing gives you this. So it means that the station number 2 must poll station number 1, must ask some jobs to station number 1 to balance the two. Okay? You apply the formula that we saw in the previous rate, and you find that alpha 21, so the polling rate, should be 0.2. Okay, so what does it mean? That when station 2 becomes idle, okay, what happens is that a timer begins with average 5 seconds. Okay? If this timer expires before a new customer arrives at station 2, this station 2 will steal all the jobs of station 1 and brings to its buffer and start working on those jobs. That's actually the behavior of this. After load balancing, you obtain that, by using the same formula that I showed you on the previous slide, rho 1 is equal to rho 2, perfect load balancing, equal to third. So if you have no load balancing, you can apply little law to the entire system that you have here, because there is no loss of customers. So you have that the expected number of jobs in the system is the sum of the expected number of jobs of this station and this station. It gives 5.5. So the expected response time that you can apply by little law is 2.75 seconds. Okay. Once you've done the load balancing, okay, you have that the expected number of jobs here and here, the total expected number of jobs is 4, and the response time, expected response time, moves from 2.75 seconds to 2 seconds, thanks to the migration of jobs that you do when there is this idle situation in station number 2. Okay, so this is basically. I repeat, I'm showing on this simple thing, but the network can be arbitrary big and complex as long as if you want it closed, you have then the problem of the normalizing constant, the usual things that people working on design knows that they have to care about.
Yeah. One question. So when you have a more complex, here you can identify which Q's have an alpha which is
Yes.
positive.
Yeah.
But so is it based on a ranking of the load factors, or what is the set of Q's which have an alpha positive in the?
Okay. Great question. Maybe I repeat because people from home. So the question is, okay, but if I have a more complex network, I don't know which station is more load balance, more loaded, and which one is less loaded. So who should you poll with? And that's actually a great question. So what we do is that every time we want two stations to have the same load factor, we allow them station 1 and station 2. We allow station 1 to poll station 2 and station 2 to poll station 1. When you solve the system of nonlinear equation, okay, this will give you 0 on the station that is less loaded, sorry, on the station that is more loaded, and the number that you care about the station that is more loaded. So the trick is that when you want to pair station, in principle, you allow both stations to poll each other. And then when you solve the system on nonlinear equation, the solution that you get will actually tell you who has to poll with. Because, that was the end of the answer.
How does this generalize with 3, 4, 5?
Yeah. So if you wanted to do, you have to pair them, you have to do them pairwise, but you can create a pair, another pair, and then all three will have the same load factor.
Okay. And then this doesn't depend on the order of pairing.
Yes, exactly. Yeah.
You trigger the mechanism when the queue is empty.
Yes.
Which means that you are going to lose some work. Why not triggering it when there is one job in the queue or a threshold that you will optimize?
Yes. So I repeat also the question because it's also very interesting. So we are triggering the polling when the queue is empty. Okay. The question is, why don't we set a threshold below which we start the polling and above which we decide that I keep this? Because when I reach the idle state, I still wait for the timer, let's say, interpret this, and it means that the server remains idle for a certain amount of time. Okay, the answer is twofold. And the first one is that if we use the threshold, if the goal is obtaining the same load factor, that is basically what we are able to observe in when we do the stationary analysis, okay, we wouldn't be able to do better than this. I don't know if it makes sense, but if I set the threshold, what can I expect to do better than reaching the fact that the two stations are with the same load factor? I'm able to look just at this. Makes sense?
Yeah, what I'm saying is that you also want to optimize the global capacity of the system, right?
Yeah. I understand that would be to do this. Actually, there is some works doing that, but in this case, you lose the analytical tractability of the system. I think there is some works by Van Hout on this threshold policy with a very specific topology that is a ring topology in mean field regime. And in that case, it does the optimization of the threshold. In this case, we may improve the system utilization, maybe the response time, I guess, on the utilization by introducing the threshold, but in that case, we would lose the analytical tractability.
Thank you. And my second question is, depending on the system you are modeling, you may have a cost on moving a job from one queue to the other, right? Is it possible to integrate this in the model?
So we can estimate the cost of migration. So we know how many jobs will migrate on this because one of those variables that you saw there in the nonlinear system represent exactly the throughput, let's say, between the line of migration between one station and another station. So the cost of migration can be introduced for optimization purposes. So in this case, it's yes.
Thank you.
Questions? Okay. So these are the take-home message. Yes, the load balancing is like a receiver initiated, and so it's actually what we obtained. And when you have the closed queue network, you obtain basically a Jackson-like product form. So if you want to study expected number of jobs or whatever, and the network is closed, you may run your MVA algorithm, but just using the load functions that are obtained after this type of optimization. And so MVA or convolution, whatever you are more familiar with, that applies also to this network to find to solve the problem of the normalization constant. And yes, the nonlinear system of equations may be tricky to solve, and so we developed these iterative schemes that is not so thrilling, but it works pretty well to find the solution of the model. Okay, so let's see another mechanism. So in the other mechanism, maybe we are a little bit closer to what you were proposing. So let's not leave the station idle. Okay, so again, the model works for general topology. I'm going to present it just for the tandem because it's simpler and we have a simple intuition. And the idea is this. Suppose that this station becomes idle, okay? So that this station becomes idle, okay? So what does it do? It goes to the previous station, okay? It takes a job from the previous station and it brings it to this station over here. However, this means that the job that is here doesn't experience the service in this station, but moves to the next station, okay? So it means that in this case over here, okay, the job that arrives here and leaves from here may have faced the service only to a subset of the station that you may have in this line of work, okay? The model in the tandem way has been proposed by Gates and Warscott to study wheel of trains, basically. And so here you have the wheels that are the bigger wheels, and then they are reduced to this one. And when you don't have any more wheels to replace, to serve a train, what you do is that you take a bigger wheel and you get it ready to work for this stage over here. What we did is we generalized for any topology of the network, so cyclic, open, closed. Okay, so let's see the advantage. If this is a Jackson network, so I'm going to work tandem here, you know that the stability condition is lambda lower than the minimum of the service rate of each of the stations, okay? In the case in which we have here is that lambda must be strictly lower than the last service rate, okay? And if you order the service rate if you're able to order the service rate in increasing order, you've got that the stability condition is that lambda must be lower than the maximum of the service rate. Yes.
Is the second statement obvious? That the stability condition for your policy is lambda less than UK? Is it obvious?
Is it
obvious?
So is it obvious? Yes, because I mean, for sure, this is a necessary condition because no one steals from this guy over here. So the amount of jobs that arrive is lambda. So this is clearly this. And here you may have that it's the last station must be able to serve, because the other ones if you start accumulating here, it will be stolen by the previous one. Yeah.
And so the heavy load has everybody.
Exactly.
So
Exactly. Yeah. That's
the heap.
Yes, that's a heap. Yeah. Exactly. Exactly. Yeah. Yeah.
Sorry.
And by the way, this is recursive. Should mention right now. So if this station asks for a job to this station, and this station is empty as well, okay, or it can go backward to ask until it finds a job to steal, basically. So here is a case that we don't see in the tandem that we have to solve to extend the model. Suppose that this station receives jobs both from this and this one. Who should I ask? To this station or to this station? So this is what we consider a natural choice, but it's also the only choice that we found that leads to product form. Okay, so to analytical tractability of the model, you choose the station with the intensity of the throughput of this station to this station, let's say. Okay, remember that these are always busy, the servers, they're never idle. Okay, so what happens is that here you choose with rate mu1 over mu1 plus mu2, you choose S1, and with the complementary probability, you choose S2. Okay, so you must know, I mean, you ask basically on the percentage of jobs that arrive from one or the other station. That's the one that brings you to have product form. Okay, so some notes on this routing policy. And the routing policy is state dependent because every time there is a job completion, you actually don't really know where the job that you're going to fetch is going to come from, okay? Because you may ask a job from your neighbor, then that neighbor becomes empty, so in turn, this neighbor will ask to another neighbor, okay? So it means that the movement of the job, okay, must be, if you want to describe formally the routing of this network, you would have, for a given state, to solve an absorbing discrete time Markov chain in which it tells you which is the first station with more than one job that you can actually steal the job from without triggering more requests around the network. Okay, so the routing is state dependent and maybe even complicated to describe in a formal way. There are only few results on product form where the routing is state dependent. There are some, but not so many, and this is one of the results that we obtain. So this is the expression of the product form. Again, as you see with the ARCAT methodology, you always try by guessing what is going to be the load factor. And here you have the arrivals from station K to station I, okay? That is, and you sum overall station. And here you got the departure from station I to the outside. And here you have all the fetching flows that come from other stations. So, and this gives you the load factor. From there, you derive the system of equation over here. The unknown in this equation are these x. So this instead, in contrast to what we saw before, is a set of linear equations. So it's very simple to solve. This is an example of closed network. Okay. So it means that, for example, when this gets empty, it will ask to this station a job with a probability mu2 over mu1 plus mu2 plus mu3 and so on, and the jobs move. The policy preserves the number of jobs, so you can study this system as a closed queue network. Some interesting results. I don't know if anyone of you is familiar with a queue network with finite capacity and blocking. So one way to solve the finite capacity problem has been proposed by Pittel in the 70s, and it's basically saying, okay, if you arrive at a station and this station has a saturated buffer, you just keep the service at that station and you move outside that station following the routing that would have followed a job that has been served in that station. So you just keep the station that you find full. And what we discovered is that if we can extend the result that I show you to Q networks with finite capacity and repetitive service blocking. So it means that if I find the station full, okay, I rework on the same job and then I call again another destination according to the random routing. That's the policy repetitive service that is known in the literature. And there is a duality relation between the work of Pittel and this work. So it means that we are able to transform a fetching network into a skip over network just by looking at the parameters and map the performance indices from one to the other. Basically, the idea is that what you see as a job in the Q network of Pittel corresponds to a hole, a space in the queue in the fetching queuing network. That's the basic idea. And from there, you can reconstruct how you do the routing, that it has to have an inverse direction, of course, because the holes move in the opposite way with respect to the customers. And following this idea, you can build this duality result. And we are arriving at the final remarks. So both Q network models have been studied by mean values approach or convolution, but we are not completely happy with these results in the sense that we have MVA algorithms, but this is either based on the duality relation or on the mapping on equivalent Jackson networks. What we really miss for these models is a formulation of the arrival theorem. For those who are not familiar with the arrival theorem, is that in a Gordon-Newell network and a closed product form network, when a customer leaves a station and is about to reach another station, just before entering the new station, it sees a distribution of the network, okay, the statistics of the network, which is the same network with one customer removed. Okay, so this means that you can build the recursive scheme of MVA. It's not necessary to have MVA, the arrival theorem, to develop MVA. You can develop MVA from a numerical point of view. You don't have the probabilistic interpretation of the algorithm as you have when you have the arrival theorem, but it works. Okay, what we would like to have is to develop an arrival theorem for this type of networks. Clearly here, the big problem is what it means for arriving of a customer. So when I steal a customer, do I consider it as an arrival? When I move a batch of customers in the LB network, do I have to remove just one customer, or do I have to remove the entire batch of customers that I'm moving? So all these questions, they're still a little bit, Diletta is working on this, and we're waiting for happy results. Okay, great. So thank you for the attention, and I'm open to take questions if there's any.
Questions? Perhaps to start with, I mean, it's very interesting the last this duality thing. So because this thing with that you alluded to, that you try to the next station, and as well we try is linked to the exclusion process, to the totally symmetric exclusion process, right?
Yes.
And so then what it means is that this fetching is a reformulation in particular of this dataset in particle systems.
Yeah, you can. Let's say that after we formulated the fetching before seeing the link to the Pittel network, because if you think this idea of stealing from in cascade, let's say from other station, is not obvious that it's connected to the to the skipping of Pittel. And the other thing is that the routing probability of the fetching network depends on the service rate, as you could see, because the stealing depends on this. So there is a duality, and you can actually, when we want to study a fetching network with finite capacity, we created a dual network in Pittel. For that one, we have developed the rival theorem in a general way, so we can study that, and then we bring back the result to the fetching network. So that's the passage that we do. That's why the duality is very important. But I mean, we would like to have it. The rival theorem gives you a lot of possibility, more than having the mean value of the performance indices, because it works also for the distribution, and so you can actually reason more deeply about the model. So we would like to be able to reason just on the fetching network without the necessity to look at the dual filter network. Also because it's not obvious that the translation for what regards the routing probabilities and the service rates. It's not straightforward.
And in contrast, the first thing where you probe when you are empty, I mean, so this is it linked to anything known in the literature, or is it a new? Here you link it to the second one, you link it to biduality, but is there anything like this?
So to the best of our knowledge, that was new in the sense that we never seen this kind of mechanism with product form. I mean, we saw the mechanism because we've been inspired by all the Lazowska works of this polling and so on. But we didn't see any result, an analytical result on this type of methods. Yeah.
At some point in one of your slides, you said that there is a closed form if there's some nonlinear equation for the solution. Do you have some criteria for which you know there is a solution, or you know there is no solution?
Yes, the criteria. I mean, let's say that we don't have a criteria, but we have a way to be sure that we will identify a solution. So the reasons why there's no solution, is that you ask a station that for some reasons, because maybe it poses something else. I mean, the relation can be very complicated, is more loaded than another station, and you ask this station to pose the other one. Okay. That's the reason why that nonlinear system of equation does not have a solution. So as I mentioned before, the way of avoiding this problem is always when you want to have two stations to have the same load factor, to allow one station to pull the other and vice versa. In this way, you're sure that the system of the linear equation will have a solution, okay? And it will tell you that one rate is 0 and the other one is actually the rate that you need to use.
I guess so. You mentioned that some of the motivation of these problems are data centers. So, are there algorithms of this type? Can you cook up or build algorithms that could be used in practice from this analysis, or is it more? Last question.
So I think that the first one, the LB network, could be actually be used. Maybe this can be, let's say, how to say, a model that allows you to drive a possible parametrization, because it's true that probably when you want to apply it in practice, you want to put a threshold that is not in 0 but is in 2. But still, the model can give you how the flows should go from one station to the other station. So I think that this is practicable. The second one, we are trying to work with the group that does image processing to see if we are able to model the stages of filtering of the image processing, to see if actually this type of algorithm is able to maximize the throughput of the stages of processing. But yeah, this is still a very preliminary work that we're doing.
Did I get it correctly that in the first principle, you can always balance all queues for the same with the same load factor?
Yes.
Okay. So right, and this is what you are alluding to with the recursive thing. You start with a pair, then make a triple.
Yes, exactly. And you do, yeah, exactly.